Let's move on to Chapter 4, Part C. In this chapter, we extend our study of the time value of money to include interest rates and loan amortizations, a very common application of TVM principles. There are three different types of interest rates we need to deal with. The first is the nominal or quoted rate. This rate is not used in calculations or on timelines. It is the rate that by law must be quoted to you in contracts. Along with the percentage rate, the number of periods per year must be given as well. For example, 10% per year compounded quarterly. The periodic rate is simply the nominal rate divided by the number of compounding periods per year. This is the rate to be used in calculations and on timelines. 10% per year compounded quarterly is a nominal rate. 10% divided by 4 equal to 2.5% per quarter is a periodic rate. Remember we said that on a timeline, the periods don't have to be years. With 2.5% per quarter, the periods are now quarters, so 5 years would translate to 20 quarters. Remembering the value of compounding, the future value of a lump sum will be larger the more often the compounding period. Interest is earned more often, so interest on interest grows more rapidly. This formula shows our basic future value formula modified to convert a nominal or quoted rate to a periodic rate. Note that both the rate and the number of periods changes. This example asks for the future value of $100 at 12% compounded semi-annually for 5 years. Note that the periodic rate is 12% divided by 2, or 6% per half year. The number of periods, N, is 5 years times 2, for 10 half years. This demonstrates the difference more frequent compounding can make on a lump sum investment at the same nominal rate. For $100 for 5 years, the difference is almost $8. Not a lot, but for higher investment values and longer periods, the difference can be significant. We've seen the nominal and periodic rates. A third way of quoting an interest rate is the effective annual rate, an EAR or EFF. The EAR expresses a rate as though it were compounded once a year. This rate can be used to compare quoted rates when the rates and compounding periods are different. For example, 4.85% compounded quarterly versus 5% compounded semi-annually. An EAR can be used in calculations, but is more often used primarily for comparison. This example invests $1 for 1 year at 12% compounded semi-annually. Using our modified general formula, the result is $1.1236, implying that the EAR is 12.36%. So 12% compounded semi-annually is equal to 12.36% annually. The EAR is most frequently used in comparisons. This formula will convert a nominal rate to an effective rate. Fortunately, both your calculator and Excel can do this as well. To convert an EAR to a nominal rate, or vice versa in your calculator, use the iConvert worksheet. This worksheet operates much like the CF one, but it only has 3 entries: nominal, effective, compounding periods per year. Since you have to enter 2 of the 3, clearing is really not needed. Access to the iConvert worksheet by pressing the second key in iConvert, which is above the 2. To make sure you can use the iConvert function correctly, you might try calculating these effective rates. Note that as expected, as the number of compounding periods per year increases, so does the effective rate. Though not mentioned in the case, there are Excel functions for conversion as well. Effect and nominal perform these functions. This is meant to emphasize the fact that whenever the compounding period is greater than once a year, the effective rate will be greater than the nominal rate. Compounding more often is better. To summarize when each rate is used, the nominal rate is required to be quoted and written into contracts. The periodic rate is used in calculations and can be computed from a quoted nominal rate. An effective annual rate is used to compare returns or loan rates when the rates and compounding periods are different. The final topic in this section is loan amortization, something most of you are probably familiar with. We're going to construct an amortization schedule for a $1,000 loan at 10% per year with 3 annual payments. Step 1 is to find the annual payment. For this, we're looking for the PMT of an annuity where the present value is the amount borrowed, and it's positive since we get the money. Future value is 0 since the loan is paid down to 0. Our payment, $402.11. The year 1 interest charge is simply the beginning loan balance, $1,000, times the annual rate, 10%, or $100. Step 3, given the annual payment we found in Step 1, $402.11, and the year 1 interest from Step 2, $100, our year 1 payment will reduce the outstanding balance by $402.11 minus $100, or $302.11. Step 4 completes our first year calculations with a year-end balance outstanding of $1,000 minus $302.11, or $697.89. Using this as the beginning balance for year 2, we repeat the steps for years 2 and 3. Done correctly, the ending balance for year 3 will be 0. Here's our amortization schedule shown in table form. Obviously, this application of time value of money is extremely well suited to Excel, which makes repeating the calculation steps for multiple years really easy. As most of you are probably aware, and as was shown in the table on the previous slide, each year of an amortized loan, the amount of interest goes down and the amount going toward reducing the outstanding balance goes up. Many of you are probably already familiar with amortized loans for houses, cars, and other types of loan. As I mentioned before, setting up an amortization schedule in Excel is very easy and quite useful to track a loan payoff or estimate the impact of making extra principal payments. This completes Part C of Chapter 4. Our last segment, Part D, will close out the chapter covering fractional time periods and non-matching rates and periods, some special cases of the basics we've covered in Parts A through C.